Now let's look at depth first search. Unlike breadth first search, which expands the shallowest nodes first, DFS always expands the deepest node in the frontier. How it works? DFS uses LIFO queue, which is nothing but a stack, and puts successors at front. So the most recently generated node is expanded first. Please understand, most recently generated node is expanded first, which means the search dives down one path as far as it can go, only backing up when it hits a dead end. DFS can be implemented with an explicit stack or more naturally with recursion, where the function calls itself on each child. So tree search DFS is not complete in general. So it can get stuck in loops like we have discussed earlier, arad CBU forever. But graph search DFS avoids revisiting the explored states, so it can complete in finite spaces. But in infinite state spaces, both versions can still fail if they follow an infinite path without reaching a goal. If the path is too long, infinite, then the DFS will fail. So how the DFS works? See, here the starting node is A, and then when it is expanded, it will consider its successors B and C, where B will be kind of marked first for expansion. Now, when B is expanded, then D and E are added to the stack, and D is marked as the node to expand. So the other side where C's subtree will not be expanded at this stage. So now D will be expanding to H and I. So once H has been expanded, it is a leaf node, so there is nowhere else to go. So this will be marked as in black, that means completely visited. So it will be removed from the stack. Now I will be chosen and as a right subtree or right sibling of this black node, and then there is also will be marked as black because there is nowhere else to go. It will go back to the parent D. Because we are using a stack, we can pop the parent, which will be D. And then this entire subtree is actually visited and it will be removed from the stack. Now we go to E, which is B's right child, and explore its children. So when this are J and K are visited, this entire subtree will be black, and then this B, the subtree at B entirely will be black. Then through A we'll go to C and explore the remaining nodes. Now, what about optimality? DFS is not optimal. It's not complete as well. It's not complete because it fails in infinite depth spaces, which you have already said, where in the spaces with loops. So it can be modified to avoid repeated states along path, but it's complete in finite spaces where it can explore all the nodes. So let's see the optimality. No, it's not optimal. For example, if the goal is shallow but lies in the right branch, DFS might waste time exploring the entire left subtree first. So let's go back and see here. Let's say the goal is M. So until DFS has explored the entire left subtree and visited up to here, M will never be found. Even C will not be found if C were the goal until this entire left subtree has been visited. So although it's just one level deep from the root node, this will never be found unless this entire left subtree has been explored. So DFS is definitely not optimal. So now, so if it's not optimal means it may return a solution but not necessarily the best one. So what is the complexity? The time complexity of the tree version is up to b to the power m. Okay, so if you remember, we did the calculation of total number of nodes, but here it means that if the depth is m and every node has b number of successors, so it's b to the power m is the the complexity, where m is the maximum depth of the tree. Okay, so this can be much worse than DFS, since m can be huge or infinite, because we are going down one path until we find, exploring all the children along that path. What about the space complexity? We don't need to store all the nodes. We just store all the siblings along one path. If the path's length is at most m, so b times m number of nodes we are storing. So it's a linear time. So this is a DFS major advantage. It uses very little memory, since it only needs to store a single path from root to leaf plus the siblings not yet explored. Okay. For example, at depth 16 with branching factor of 10, that means b equal to 10, BFS might require 10 exabytes for BFS, but DFS only needs 156 kilobytes, a massive saving. Okay. So now I want to tell you about a variance of the DFS, which is called backtracking search. So earlier we said that DFS in general stores the one node and all its successors, but backtracking search is a variant where saves even more space by generating one successor at a time, okay, instead of all at once. This requires just order of m times memory, so just at every level it just stores one node, plus the ability to undo actions when backtracking. So when you go back using the stack and you see, okay, there are you have to explore other paths, then you have to add some more nodes to that. But overall the worst case complexity is order of m. It's widely used in constraint satisfaction problems, SAT solvers, and logic programming. So in general, DFS is incomplete in infinite spaces and not optimal, but is extremely memory efficient, which makes it a backbone for many AI problem solving methods, especially where memory is the bottleneck.